welcome back to another Oh No, I've Got a Test in 5 Minutes Physics. So, if you're taking a look at basic waves, here is your basic formula for waves. Velocity is equal to wavelength times frequency. And so, kind of your simple waveology, and I'm going to pull a FET up again for a second here. So, I'm gonna see if I can. I'm gonna make a wave with a frequency of 1 hertz. And so what that actually tells me is, let's restart this, and here we go. I've got a little oscillator, and it's gonna go up, down, and back to this position once every second, and that's what a hertz is. And so we can kind of pause it, and I want you to take a look at the idea of the wavelength. And we don't even really see a full, let's see if we can restart again. Let's go slow motion. Let's see if we can really take a look at it and pause. I want to get it over to there. So a wavelength then is the distance between like two, not just from the crest to the crest, but we could even do from trough to trough or any two identical points on the wave. That's what's considered a distance of a wavelength. So here we got a wave with a frequency of 1, and let's do what 2. And I want you to kind of notice, so here's the wavelength in this one. Let's take a look when we change it to 2. I'm going to pause it when it gets to the end. And I want you to go ahead and notice something. Let's just do trough to trough because, or crest to crest, because that's the easiest observation. But I want you to notice what's happening to that wavelength as I increase the frequency. Now let's increase it all the way to 3 and take a look at the wave that's made at this point. I'm going to stop it when it gets to the end. And hopefully what you've noticed that as the frequency of the wave is increased, the wavelength of the wave is decreasing this entire time. And so that's kind of your basics on the wave. And so most of the time you've kind of got in the wave problem is you're going to be giving data or information regarding wavelength. And again, it doesn't have to be crest to crest. You might be asked to find questions regarding the amplitude of the wave. And most waves, we kind of do like a dashed line through the middle, and we call that a resting position. This distance, either above or below this maximum, that's still what's called your amplitude, just like you saw in simple harmonic motion. That's because a wave is an example of simple harmonic motion. Because if you think about point on, let's say that it was a point in water, as the wave passes, that point's going to go down and back up again, just like if you were floating in the water. And so this wave has a wavelength, it has a frequency. This wave also, one of the other common wave formulas you'll use is this idea of 1 over frequency. And so that's your period for a wave. And the period is actually just a measure of time, so it's in seconds. Whereas frequency, on the other hand, frequency is always measured in a hertz. But the thing is, it's a vibration per second. So another common unit for frequency is just 1 over S to represent the fact that it's something happening per second. How many oscillations per second are being made? If you're trying to look up here a couple of these other formulas in here, one of the others here, let's take a look at this one. If you are given a problem where maybe you've got like some kind of tension on there, I wonder if I can go back to my, oh yeah, I can change tension on this. So let's do this. Let's restart this one with no tension on here. And maybe we should increase the tension just a little. I want you to notice what happens to the speed of that wave as we increase tension. So obviously the things we can look at in terms of this string, one of the things is the tension that's on there. So I want to go back to this formula. So like if you've got a string, the tension that's being applied to it is a factor in terms of how fast the wave moves. This mu in this case, this is actually the linear density of, like, say it's a string or a slinky. This is actually going to also, so you can imagine that like a heavier rope is going to behave different if you're trying to, let's say you're into like the CrossFit stuff and you're going out and grabbing the giant rope and doing the whole whip thing with it. Obviously, you'll notice that the giant rope, that the density of the material that you're creating the wave in obviously makes a difference. I typically don't use that formula a whole lot. If you're looking for the speed of sound, because sound is a mechanical wave as well. It's just it's kind of hard to draw because it's made of a series of compressions, and these wide areas are known as rarefactions, but all the math is still the same in terms of how it behaves. You can use the exact same formulas for it. And so this formula, what it actually does is it tells you the speed of sound in air at TC in this formula, that's any temperature. So like at 10 degrees Celsius, we could plug that in and it would give us a speed of sound at that temperature. That's all this other formula was. It's just it used Kelvin instead of degrees Celsius. The last couple of formulas that are on here, so this is an equation to help us find frequency in a string. The L is the length of the string. Force, you could also say, is the tension being exerted on it. And of course, this is also your linear density in there, this mu, or how heavy your string is. One of the other equations comes in handy if you're talking about resonance positions in a spring. In a pipe, you can have what's known as open pipes and closed pipes. And what this formula allows you to do, it lets you find intervals of sounds. If you've ever, this is hard to do in the video, but what it lets you do is at any length of pipe, it lets you find a resonance frequency that would exist for a pipe of that length. The V in it is just that is your speed of sound that's present in there. And here's what's neat about pipe. You get these resonance positions at different intervals, but you'll notice something. The counting method in an open pipe goes 1, 2, 3, and in a closed pipe, it goes 1, 3, 5, 7, 9. Hopefully, you've got the idea. So, a little bit of difference. And so, a closed pipe is when you have a pipe that literally is closed on one end. So, you put a wave into the pipe, it bounces off, and boy, this is not my best wave. There we go. And so, you've got this point at the top where you've got uh, you're going to hear a loud sound coming out of it, and we just call that resonance. And so an open pipe would be a pipe that's literally open at each end. So it'd be like you have a wave goes in, and that wave on each end of the pipe, you've got what we call an antinode. I never said that in the video, by the way, but when you're looking at a standing wave in a string, the math, of course, just uses the same equations we've already done. But standing wave, we call these points up here, we call these antinodes and nodes. So if you have trouble remembering that, a node, we just remember a node has no vibration at the node. So the antinodes are these points where you have a maximum amplitude being present in there. And so the formula to use to this standing wave is the formulas you've seen over here as well. So anyway, I know this is again rushed, but hopefully it gives you a little idea what all the formulas are in this unit. So I hope this helps you out, guys, as you work the problems dealing with velocity and waves. Bye, guys.